Hello, welcome to another video of Dr. Webb's on graduate level mechanics. So in this video, we shall be focusing on a very simple example of free motion on a cone. This cone here is held fixed by some means, and what we have is a bead or a small particle constrained to be on the inner surface of the cone under the influence of a constant gravitational field. Now, what are the possible motions that can be experienced by this particle is our ambition of studying. Now, the first thing we'll do is dismiss the Newtonian analysis very quickly. There's only very limited things that a Newtonian analysis can give us, and that will be circular orbits. It's a good thing, though, to do the Newtonian analysis first so we know what to expect in the more advanced treatments. The Lagrangian analysis, we shall incorporate the constraints, we shall enforce the constraints using Lagrange multipliers and see how the specific shape of the constraint that we have will affect the type of force that we end up identifying. So constraints are very sensitive in that sense. Finally, we'll move on to Hamiltonian analysis. We'll study the problem. The great advantage of Hamiltonian analysis is it provides existence theorems on bound orbits. So that's what we'll see. Then we'll show how to assess stability. You can show the stability for any bound orbit, but I'm going to show it for circular orbits only. And then obtain a really cute quantization criterion for closed orbits. Now, this should recall, for those who have studied quantum mechanics, the early days of quantum mechanics. Well, what they used to do was they used to take classical mechanics problems and apply what's known as the quantization condition of Bohr and Sommerfeld to convert a classical problem to the corresponding quantum version. So you can think of this as a quantum particle trapped in a cone of some nature, and it would then be quantizable by this criterion. So that's a lot of stuff. Let's get going, starting with the Newtonian approach. In this approach, we start off by drawing free body diagrams. So I'm going to draw the cone again. The half angle of the cone is specified as theta, so that coordinate is off limits. Let us instead use the coordinate phi for the circular coordinate. So that angular velocity of the particle is phi dot at any given time. Now that's your particle of mass m. The two forces that are acting on the particle are gravity acting straight down, and the normal force, which will always act perpendicular to the surface of contact, like so. Now let's quickly look at the angles involved. If I draw a perpendicular coordinate system here, then it's clear that this angle is also theta, which means this angle will be 90 minus theta, making this angle theta as well. So those are the angles. Let's have the coordinate system. The rest of the coordinate system is the z direction and the r direction. We are in the cylindrical coordinate system. So if the r direction is radially outward, the negative r direction is radially inward. And that's true here also. Just something to keep in mind. Now we can write Newton's law in both the z direction and the r hat direction. The sum of all the forces in the z direction is 0. And we're going to only do circular orbits for the Newton's analysis. So I'm going to just assume that we're already in a circular orbit. To emphasize that, I'll draw a circular orbit here. So this gives me the forces in the up direction are Fn sine theta, and the force in the down direction is mg. So I get my first equation, which is Fn sine theta is equal to mg. Let me save that. Now I don't make any claims to keep track of my equation numbering, so here's to hoping the universe supports me. The sum of all the forces in the negative r hat direction, which means in this direction where the bead is located, is given by mass times the centripetal acceleration, r double dot. Well, let's see what that gives us. Fn cosine theta is going to be the centripetal acceleration times the mass. The centripetal acceleration is omega squared r. Well, that's just r times phi dot squared. And because I'm in a circular orbit, I'm going to choose r equals r naught, and I'm also going to assume that at a fixed radius, the angular velocity is also constant. These are assumptions for circular orbits. As a result, my second equation becomes Fn cosine theta equals m r naught phi dot naught squared. Equations 1 and 2 can be simultaneously solved. First of all, notice that from equation 1, I can immediately grab my normal force. So the normal force Fn is just mg divided by sine theta. Let me box that. And we're going to use this to compare what the Lagrange parameter gives us in method 2. So let's save that result. We'll need it later. Now you can either put this in there, which let me just do that. So if I substitute for Fn in there, I'll get mg cosine theta over sine theta, which is mg cot theta. So mg cot theta is equal to m r naught phi dot naught squared. The mass cancels on both sides. So you can think of this as another version of Galileo's result, except inside a cone. And now we can solve for the stable radius r naught, which is always good to have. So you can either solve this for r naught, or you can solve this for phi naught dot, or the angular velocity, it doesn't matter. So I'll get my radius. Observe it as the right units, because g is meters per second squared, and phi dot squared is 1 over second squared, so you end up with meters. And that really finishes our Newtonian analysis. You can't really do much more with Newton's methods. Now let's go to the Lagrangian method. In the Lagrangian method, you have to first form Lagrangian, but there's also a constraint involved here. The Lagrangian is going to be a function of several variables, the z coordinate, the r coordinate, the phi coordinate, but z and r are not independent. Because all the motion is occurring on a cone, we have to find the relationship between those variables. Let's draw a little triangle to help us. If you're going to be on the cone, that's your z, that's your r, that's your theta. Let me just call this slant height L. Then immediately we notice that z and r are locked into a relationship from the very beginning. So that relationship must be maintained at all times if the particle is not to leave the cone. So we can write this as r over z equals tan theta, because that's the first thing that comes to my mind when I look at this triangle. So I can write my constraint, which is g of r z phi, possibly time, but there's no time here, as r minus z tan theta, and that's equal to 0. Now that constraint equation, now all we have to do is write the Lagrangian in the coordinate system known as cylindrical coordinate system. The Lagrangian can be written as follows: t minus u. In an earlier video, I showed you the kinetic energy term in the cylindrical coordinate system is just r dot squared plus r squared phi dot squared plus z dot squared minus the potential energy term, which I'll write as mgz. So I'm making a choice right away in writing that potential energy term, that my ug is down there. So if my ug is there, then the z coordinate is going to be in the positive realm. So because ug is positive mgz, you do get a subtraction sign. Now, once a Lagrangian has been written, we can now use the Euler-Lagrange prescription to solve the various equations. There are three equations, one for r, one for phi, and one for z. So let's just mention that the Lagrangian is a function of r dot, phi dot, z dot, and time. Let's just take a look at this. R and r dot are both there. Phi is not there. Phi dot is there, but phi is not there. So we can expect some conservation principle coming out of there. It will turn out to be angular momentum conservation. Z and z dot are both there, and t is not there. So we can expect a conservation principle to come out of that. That will be energy conservation, which will help us in the Hamiltonian approach. So all this we can just get by staring at the Lagrangian for a few minutes. Now, let us write Lagrange's equations. These are just given by the following prescription. The R equation is d by dt of del L over del R dot minus del L over del R plus lambda times del G over del R equal to 0. Now, all we have to do is differentiate each term. Del L over del R dot is 2r dot, so that cancels with the half there. And then when I take the d by dt, I get r double dot. So I get m r double dot minus del L over del R. I just pick up 2 here, 2r, but that 2 cancels with the half. So I get m r phi dot squared. And then plus lambda times del G over del R. That's just 1. Let me call this equation 1. Our next equation is going to be the equation in the phi coordinate. Let me write that. It's d by dt times del G over del phi. It's a good idea to write this each and every time so you know what's happening. Now, immediately we notice that L does not depend on phi. We already made that observation earlier, so that's 0. G doesn't depend on phi, so that's 0. So d by dt of that quantity must be 0. Now, this, incidentally, is the canonical momentum associated to the angular velocity. So this is telling us that the canonical momentum corresponding to that variable is cyclic. So pi phi, which is del L over del phi dot, is constant. Now, what is del L over del phi dot? Observing the Lagrangian, that is just going to be m r squared phi dot. So we realize that m r squared phi dot must be a constant. Now, this constant is mr squared omega. Well, that's just the moment of inertia times omega. That's the z component of the angular momentum. So this is just LZ naught. So I'm going to keep that as a reference. The z component of the angular momentum is always constant. Now, by the way, this does not mean that it's a circular orbit. So far, I've made no restrictions on the type of orbit. It could be any orbit. For example, let me draw a picture here quickly to dispel any confusion on that respect, I have here the cone, and a particular orbit we can be looking at could be this. Okay, so I could have a situation where you go at a very low radius, which is here, to a very large radius, relatively speaking, which is that. And this quantity is always constant. So what happens is when r is small, the particle is swinging by really fast. And when r is big, it's swinging by slowly. So you can think of this as a Kepler's law, second law. Okay, Kepler's second law is in fact the same as these types of equations. So this is essentially Kepler's second law for this problem. And some of you may have remembered that from your school days. It says that equal areas are described by the planet in equal times. Here, of course, there's no planet, it's just a bead, and there's no sun, it's just a z-axis. But you have a Kepler's second law nonetheless. It's always a conservation of angular momentum that leads to Kepler's second law. Lastly, the z equation. So let us look at that. The z equation is the following. So once again, we look at this equation, and I'll just get the term mz double dot. And then del L by del Z, I just pick up this, but with a negative sign and a negative sign here, it becomes plus when I do the double negative. And then lambda times del G by del Z, I get negative tan theta. So negative lambda tan theta equals 0. I believe I've already violated my rule of numbering. If that is 1, okay, this is 1 and 2 for the Newtonian method. That's 1 and 2 for the Lagrangian method. So each method will have its own numbering system. Let's agree on that. So that's 2, and then this is going to be 3. That way I don't have to carry the numbering system across different parts. Now we just have to solve. Now this is a very general system. As you can see, it's far more general than Newtonian. For example, it can describe orbits like this. So what we do need is a circular orbit. So let's specialize to steady state circular orbits. What that means is you don't vary in the z direction like here. So you definitely don't vary in the z direction. We have to set z double dot equal to 0. And you also don't vary in the r direction. Actually, if you notice, if z double dot is 0, then r double dot must be 0 because they're tied together by this constraint. So you don't independently have to say those two things, but I said it anyway. They're tied together. So now let's go to the steady orbits. When I put r double dot equal to 0 there, and then also let me agree that r naught is a radius and phi dot naught is the angular velocity for the circular orbit. So now I'm going to end up getting that equation is going to give me negative m r naught squared phi dot naught. Sorry, there's no r naught squared. There's just r naught times phi dot naught squared plus lambda equals 0. So I immediately get what my lambda is. Okay, so that gives me my lambda. Lambda equals m r naught phi dot naught squared, which is good to have. Let's just keep it and see how we can use it. I'm afraid to number it because if I do have to remember it. the number. So the other thing you can do is this equation. Mz double dot is 0. That equation there will just tell me that. So let me also look at I'll call this 1 prime, 2 prime, because these are just the equations 1, 2, and 3 with the circular orbit condition put in. So now I get Lz naught equals m r naught squared phi dot naught, and 3 prime, the z equation, becomes mg equals lambda tan theta. Now it's a good time for us to compare with our Newtonian framework. In the Newtonian framework, mr naught phi dot naught squared was precisely fn cosine theta. So lambda is fn cosine theta. It is only a component of the constraint. Okay, so I'll write here only component of the constraint obtained. Let's come back to that. Right now, let's focus on this. I get mg equals lambda, which is equal to that. So I get m r naught phi dot naught squared times tan theta. And that immediately, upon cancellation of m's, gives me the criterion for the radius of the circular orbit. And that is given by this equation. And it's the same as the Newtonian second law. So it agrees with the Newtonian second law. There, you only get a component of a constraint. Now, here's a philosophical talk. What is the role of constraints in this problem? Now, I wrote the constraint as r over z equals tan theta. Well, let us suppose a little Tweety bird had told me, don't write the constraint like that, write it as something else. So I'll listen to that voice and write my constraint this time as the following. We'll write the constraint as g equals r cosine theta minus z sine theta equal to 0. Now you may think this is certainly not very clever, because all I've done is written tan theta as sine theta over cosine theta. And then once I write tan theta as sine over cosine, I just multiply the cosine to the left and the sine to the right. And then I just get r cosine theta equals z sine theta, which I then write as r cosine theta minus z sine theta equal to 0. But let's just suppose inspiration had struck me in that direction. Then what would have happened to all my equations? The basic parts of the equation will remain the same, but only things that would change are those parts. So let me rewrite all the equations I'll get. So equation 1 double prime would have been mr double dot minus mr phi dot squared plus lambda times del g over del r, which is now cosine theta. And then the equation 2 double prime would not have changed, so I won't bother writing it. The equation 3 double prime would have been the following: mz double prime plus mg. And this time, when I do del g over del z, I'll pick up negative sine theta. So negative lambda sine theta, that's equal to 0, that's equal to 0. So when the orbits are circular, you don't have this, you don't have this. The first equation gives me mr phi dot squared equals lambda cosine theta. Now, I compare that with Newtonian, and I'm immediately home free. Mr phi dot squared is indeed lambda cosine theta is equal to Fn cosine theta. So this gives me lambda equals Fn. Now, let me just assure you that writing this constraint in this slightly different way has not messed with our answer. So what I'll do here is I'll use lambda value from there and substitute it here. So I get mg equals lambda sine theta from the equation 3 double prime. And now I'll take lambda from there. So I get mg equals lambda, which is m r naught phi dot. These are circular orbits, so I'll put naught now. Phi dot naught squared divided by cosine theta, because lambda has got a cosine theta multiplied with it, times sine theta. M's cancel out. And then I immediately get R naught equals G over phi dot naught squared times cot theta. It is exact. So that criterion is not messed with. So this criterion is got, and now we agree with Newton's second law in both places. So this advises you something very important about constraints. It is entirely your luck that determines if you get the correct constraint or not. So I'll say constraint determined. The constraints form determines the constraint force. Something so simple as writing tan theta as sine theta over cosine theta resolved the issue of not being able to see the constraint force. So now we have solved this problem using both the Newtonian and the Lagrangian method. Our main focus and the majority of this video will be spent on the important analysis, which is the Hamiltonian analysis. So for the Hamiltonian method, we have to go through a number of steps to obtain the Hamiltonian. So let's do that. The first step is to form the minimal Lagrangian. Well, the minimal Lagrangian is defined as a Lagrangian with the constraint incorporated. I'll put the original Lagrangian over there. To form the minimal Lagrangian, you really don't care how you write the constraint. So the first step is the minimal Lagrangian. So let's just use the constraint as we originally wrote it. So we incorporated. What's meant by incorporating it is the following. It means you remove one of the variables. I'm going to write z as equal to r cotangent theta, because I somehow don't want to see the z variable anymore. When I write r equals z tan theta, I can write that as z equals r cotangent theta by taking the tangent to the denominator. So that tells me immediately that z dot, because theta is fixed, the cone angle is not changing, z dot is r dot cot theta. Now, if you were having a problem in which the cone angle is changing, this was where you would incorporate that too. So a lot of things are possible in this approach. So now we'll incorporate it, which means we'll write the Lagrangian without any z anymore. So L min is going to be 1/2 m r dot squared plus r squared phi dot squared plus r dot squared cot squared theta minus mg z, which is r cotangent theta. So that's our minimal Lagrangian. We can do one small simplification step. 1 plus cotangent squared is cosecant squared theta. So I'll write this as 1/2 m r dot squared cosecant squared theta plus r squared phi dot squared minus mgr cot theta. The next step is to write the canonical momentum. I like to refer to the canonical momentum set as pi can. So now Let's do that. The R canonical momentum PR is del L min. I'll stop writing min. Del L over del R dot. So let's just look at that and differentiate. That's just going to be m cosecant squared theta R dot. And then the canonical momentum corresponding to the phi coordinate is del L over del phi dot. And that's going to be m r squared phi dot. Now this immediately leads us to the next step, which is the Legendre transformation. The Legendre transformation is just fancy name for writing the generalized velocities in terms of the generalized momenta. In this case, it's easily done by simple division. So this gives us R dot is PR over m cosecant squared theta, and phi dot equals p phi over mr squared. Now that we have done all the preliminary steps, the Hamiltonian itself can be written. So that's the next step. The Hamiltonian H is equal to PR times R dot plus P phi times phi dot minus the Lagrangian L, which is a function of R phi, the minimal Lagrangian, that is, R dot and phi dot. It's not a function of time, so I won't write it. The thing that you should be kept in mind in this case is that all of these things should be in terms of the canonical momentum. So I'll just write pi can as a reminder. Okay, all of these should be written in terms of the canonical momentum. So that's where all the algebra is. So let's do that algebra. So the H is going to be PR times R dot, which is this. So I'm going to get PR squared over m cosecant squared theta. And then when I put phi dot from here into there, I get p phi squared over mr squared minus the Lagrangian. The Lagrangian, minimal Lagrangian is right here. I'll substitute for r dot squared. So I'll multiply half m into each term. So I get half m, r dot squared is that, squared, m squared cosecant 4 theta in the denominator, times cosecant squared theta, let's not forget that. And then the next term, while it's still within the flower bracket, the next term would be given by, I'm taking the 1/2 inside, so it's going to be 1/2 m. I'll put the r squared first, times phi dot squared. So that's going to be p phi squared over m squared r to the 4. And then I'll close the flower brackets now. But then you also have a potential energy term, which is negative, and the negative sign here, so that becomes positive. mgr cot theta. So at this point, I can simplify this. I realize at once that the cosecant squared and cosecant 4 give me a cosecant squared mass and cancels out. And this is just 1/2 that. Similarly, I cancel out m here and an r squared with r to the 4, and that is just half of that. So I'll end up getting the Hamiltonian to be PR squared over 2m cosecant squared theta plus p phi squared over 2mr squared plus mgr cot theta. So that's a important milestone. Let's box it. We've got the Hamiltonian entirely in terms of the generalized coordinates and the canonical momenta. The next step is Hamilton's equations. Now, two of those equations are what I like to call static, meaning that you get back the Legendre transformations. So let's work on that. R dot is del H over del PR. The advantage of doing these is to make sure you did have all the work right up to this point. So I get PR over M cosecant squared theta, which recovers the first Legendre transformation, and then phi dot, which is del H over del P phi. That gives me P phi over MR squared, and that recovers the second Legendre transformation. So we have successfully recovered them both. Now we proceed to the dynamical Hamiltonian equations. There are actually three of them. I'll focus. One of them has been given a short shrift. Up to this point, I'll focus on that too. What are the dynamical Hamiltonian equations? The first one tells you that PR dot is negative del H over del R. Well, you take the Hamiltonian and differentiate with respect to R, I only get contributions from the second term and the third term. Here, when I differentiate R squared, I'm going to get negative R to the R cubed in the denominator, and the 2 disappears. But the negative sign is canceled by the negative sign here. So I just get P phi squared over MR cubed. And then here I get negative mg cot theta. So that is an important equation. I'm going to call that equation 1 in the Hamiltonian section. That's equation 1. Then I also have P phi dot, which is negative del H over del phi. Observe that there is no phi coordinate in the Hamiltonian. So that immediately tells me that P phi must be the z component of the angular momentum, and it's conserved. So that's going to be mr squared phi dot. So that gives us the same equation that we always had in all three approaches. This is, by the way, this and the next are instances of a very famous theorem in mechanics known as Noether's theorem. Noether's theorem says to every cyclic coordinate is associated a conserved quantity. The cyclic coordinate phi has associated to it the angular momentum, which is conserved, and the cyclic coordinate time is going to have energy associated to it. So the third Hamilton's equation is dH by dt is equal to del H by del t. In other words, the total derivative is equal to the partial derivative. Now the partial derivative with respect to time is 0 because I don't see it anywhere. So that's going to be 0, which tells me that dH by dt is 0, or that means that H is constant. That constant, let's call it E naught. E naught is the total energy that you have pumped into the conical mass system at any given time. Now, with this energy available to the mass, why doesn't it go crazy and do crazy things? Well, our next study is to study the bounded orbits. So that's what we're going to do next. We're going to study the existence of bound orbits, and then we're going to assess the stability of the orbits, and lastly, we'll obtain a quantization criterion. So those are the three things we'll be doing with the Hamiltonian approach. So let's keep this Hamiltonian handy to investigate bound orbits. We will use the second Noether's theorem over here, that energy is fixed, and write the Hamiltonian as follows. I'll write it as E naught is equal to PR squared divided by 2m cosecant squared theta plus LZ naught squared. Now I'm using the first Noether's theorem over there in the numerator over 2mr squared plus mgr cot theta. So I've incorporated the results of both Noether's theorems and got this equation. Now this equation is pretty awkward to look at and to work with. So I'm going to make some immediate scalings. I'm going to call a new kind of radial momentum as follows. It's the square root of 2m cosecant theta, some sort of scaled radial momentum, if you will. And also I'll call beta to be LZ naught squared over 2m, since that's all a constant. And then alpha I'll call mg cotangent theta. So that makes our equation look a little bit cuter. So I get p prime squared plus beta over r squared plus alpha r. All right. Now, motion is stable if in a graph that you draw, turning points appear. That is, the motion is bounded between r plus and r minus. At the turning points, the radial momentum is 0, because that's when the particle goes from r stops and then turns around. Okay, so we want to prove the existence of the turning point. Roughly speaking, let me draw a graph, and we're trying to prove that this graph actually happens. So here's my wishful thinking. I want to show that there is some graph like this that actually appears in this problem. Don't worry about the shape of the graph. It's going to look like a parabola because that's the only graph I'm capable of drawing. But generally, it's more complicated looking than that. And then I have some energy, fixed energy E naught, which is over here. So what I want to show is the existence of these turning points. I'll call this R minus and R plus for the obvious reasons. Minus is less than plus. And then there's a specific point where R minus and R plus converge into a double root, and that I'll call R0. That'll be our circular orbit. Okay, and the circular orbit typically has negative energy in some problems. In this problem, of course, it's got positive energy. So I should have drawn the whole graph above the r-axis. There's no intersection here. I was thinking of real life in atomic physics and things like that. You do have negative energy for stable orbits. But in this artificial problem, the energy is always positive. So just keep that in mind. All right, now let us also, I want to do the following. To find the turning points, I'll set the radial momentum equal to 0, or the scaled radial momentum equal to 0. They're defined as points where that happens. And so my equation looks a little bit simpler. E naught equals beta over r squared plus alpha r, where beta is positive and alpha is positive. Just keep that in mind. Now, we can rewrite this equation as follows. I'll multiply the whole thing by r squared, so I get alpha r cubed, and then bring the E naught to the right side. Well, E naught gets multiplied by r squared plus beta equal to 0. That's known as a cubic. We don't know what alpha, E naught, and beta are in general. All we know now is E naught, alpha, and beta are all three positive. So we can create a little sign table for Descartes' rule of signs. Which I don't know if you have studied in your elementary grades. It's a method by which you can assess, give existence proofs for the number of solutions to a equation of high degree. Here are the positive root solutions, negative real solutions, and complex solutions, which I indicate by the symbol I. The rule of signs tells you how many sign changes you have in going from the one highest coefficient to the lowest coefficient is the number of roots you have. So let me show you how that works. If I go from here to here, I have one sign change because I go from a positive alpha to a negative E naught. And then I have a second sign change because I go from negative E naught to positive beta. So I have two sign changes. Well, once you have the third degree equation can only have three roots. So complex roots are ruled out because complex roots always occur in conjugate pairs. If I have to have some entry there, it has to be either 2 or 0. So 0 is the only option, which means there's one negative root. So this rule of signs has taught me that there's another branch on this side, which I'm not worrying about because negative R values don't make any sense in my world, in this coordinate system. The other thing the rule of signs will tell you is you can get this value also by doing the following switch. You can change R to minus R. So that gives me negative alpha R cubed minus E naught R squared, because when you change R to minus R, R squared doesn't change its sign, plus beta equal to 0. This is just a phantom equation for the rule of signs. Here to here, no sign change. Here to here, one sign change. That's how the one can be fixed also. Okay. So otherwise, please ignore this equation. This is for the Descartes rule only. The other option you can have is the number of positive roots can drop by 2. Then the 2 has to be over there. Well, unfortunately, we don't, or fortunately, we don't have that situation. That situation will only happen if you have E naught to be less than 0, for example. So we're not worried about this situation. Now, what happens when R minus and R plus coincide? It's still 2 roots, except it's a double root. So this captures all the 3 important things we have. And so we have actually shown that stable orbits exist. We've shown that stable and circular orbits exist. You can, of course, simply draw the picture and say, hey, believe it, it exists. But this is a more formal way of looking at it, okay? Now, this is all true for beta not equal to 0. That is to say, the angular momentum is there. What if there's no angular momentum? Then what kind of orbits do you have? So we have to worry about that also, because this is a general treatment. So let us talk a little bit about that. If beta is equal to 0, now if the beta for the Earth were equal to 0, it'll go and plunge into the sun straight away. So that's something like that we're thinking of here. LZ naught equal to 0. Then what happens? Well, first of all, our equation becomes a little bit simpler. E naught is PR squared over 2m cosecant squared theta plus mgr cot theta. We lose the term in the middle because it's no angular momentum. Now I'm going to go and put back the Legendre transformation. So PR I'll write as r dot times m cosecant squared theta. So I'm going to get 1/2 m cosecant squared theta r dot squared when I do that and simplify, plus mgr cot theta. Now we know that the rate of change of energy is 0, because that's what energy is conserved means. So this gives me m cosecant squared theta r dot r double dot plus mg cot theta times r dot. So we have two options, either r dot equals 0, which means r doesn't change. Well, that is a peculiar circumstance, and it won't happen. Okay, so I'll just dismiss that straight away. The other possibility is that m cosecant squared theta times r double dot is equal to negative cot theta times mg. So the m's cancel out, and I'm left with r double dot equals negative g. Cot theta is cos theta over sine theta. And cosecant squared, when brought in the denominator, becomes sine squared in the numerator. So I just have this weird looking result. To see if it makes sense, let's go back to the triangle that defines the conical geometry. You have here the r coordinate, the z coordinate, and the length, slant coordinate, slant length, which I introduced initially. Let's worry about the slant length this time. R over L is precisely sine theta. So this tells me that R double dot is equal to L double dot sine theta. Or in other words, if I write L double dot sine theta here, the sine thetas will now cancel. So I get L double dot equals negative G cosine theta. But that is exactly what you expect. The rate of change of L in this direction is a component of gravity along the slant height, and the component of gravity is precisely G cosine theta. It's not G sine theta, it would be G sine theta if the angle theta were here, but the angle theta is with the vertical. So the component of gravity is G cosine theta. This tells me that if the angular momentum is not there, the bead simply slides down with constant acceleration given by G cosine theta. So this completes the investigation of orbits for both zero and non-zero angular momentum. Our next aim is to see how perturbation is carried out. I could do the perturbation analysis for general orbits, but I've been asked to do it for circular orbits. So let's do the circular orbit perturbation. All right, so for circular orbits, we have R equals R naught, phi dot equals phi dot naught, okay, and PR dot equals 0. This is not perturbation yet, it's circular orbits. When are circular orbits possible is what we're going to look at first, and then we'll find the criterion for circular orbits and then perturb them. So PR equals 0, and P phi must be equal to LZ naught, which is equal to MR squared, R naught squared, phi naught dot. So I'm copying all this from here. For circular orbits, that becomes R naught, and that becomes phi naught dot. Okay, now we'll put this in the dynamical Hamilton equation, which is right here. So put in 1. Except, I'll just do it. Let me do this. So 0 equals P phi squared, which is LZ naught squared over M R naught cubed minus mg cot theta. So that equation can actually be solved. We're going to solve it for the stable radius, R naught. So I get R naught is equal to, I'll bring this everything downstairs and then take the cube root. So that's going to be LZ naught squared over that M becomes M squared when it's brought downstairs. So M squared G cot theta, the whole thing to the power 1/3. So that's our stable radius for a given angular momentum. Let's also find the orbital period, because the orbital period will help us address the quantization criterion. Okay, so we're going to find the orbit period next. So let me comment on what this is. This is a stable radius for given angular momentum. Now for orbital time, all we have to do is find out how much time it takes to go around once. So that's easily got. I'll call it tau orbit. For a circular orbit, it's tau orbit naught, and that's just going to be 2 pi over phi dot naught. But phi dot naught is right here. So that's going to be 2 pi m r naught squared over LZ naught. Because phi dot naught is LZ naught over mr naught squared. Okay, now I can substitute for r naught squared from there, and you can write the orbit period in great detail. I won't bother doing it. Now I'm more focused on the perturbation. The perturbation has two parts. You can perturb the radius, and you can perturb the angular speed. Both of those things should be looked at in a perturbation analysis. So let me write down the two things to be perturbed: the radius, and two, the angular speed. For a circular orbit, the radius is fixed and the angular speed is fixed. But if you perturb it, both of those two things will change. And we have to assess if the change is stable or unstable. So the stability of perturbation is what we are up to here. Let me first do the radial perturbation. So r is now going to be r naught plus epsilon. You're nudging it a little bit. So r dot is going to be epsilon dot, and r double dot is going to be epsilon double dot. Well, no longer can you write the dynamical equation like that. You have to you can't put PR dot equal to 0 anymore. So I'll write this as PR dot equals, I'll just copy it down. This is LZ naught squared, because P phi is still LZ naught, over mr cubed minus mg cot theta. I'm going to use a Legendre transformation to write PR in terms of r dot. So let me do that next. When I write PR in terms of r dot, I get m cosecant squared theta times r dot, and I take a derivative, it becomes r double dot. So that's m cosecant squared theta r double dot equals LZ naught squared over m r cubed. Well, for r cubed, I can write that as r naught cubed times 1 plus epsilon over r naught, the whole thing cubed. Okay, all I've done is taken r naught outside and written it like that, minus mg cot theta. All right, r double dot is epsilon double dot, so let me immediately put that in. What happens here? I can take this to the numerator. Let me do that first. So LZ naught squared over m r naught cubed, 1 plus epsilon over r naught to the power minus 3 minus mg cot theta. Up to here, everything's exact. But remember, the essence of a perturbation is that the perturbed quantity is small. So somehow we have to talk about the smallness. Smallness is enforced as follows. The absolute value of epsilon is much less than r naught. So that's how we enforce smallness. If we have that criterion, then we can use Taylor's theorem or Newtonian's binomial theorem and write this as follows. I get m cosecant squared theta epsilon double dot is equal to, or approximately equal to, LZ naught squared over mr naught squared, cubed, excuse me, times 1 minus 3 epsilon over r naught. So that's the approximation I've used, mg cot theta. Let me just write the approximation here. I've used approximation 1 plus x to the power n is approximately 1 plus nx if absolute value of x is much less than 1. Because epsilon is much less than r naught, epsilon over r naught, which is going to be my x, is indeed much less than 1. So it's satisfied, and that's legitimate. Okay. So let me write this now. Now for circular orbits, we already have the criterion there for circular orbits. In fact, we have this. going to call this equation star. So from star, I already have LZ naught squared over M R naught cubed is equal to mg cot theta. In other words, I can remove this annoying thing and write mg cot theta instead. That's an improvement. So I have m cosecant squared theta epsilon double dot is approximately equal to mg cot theta. That's that term minus 3 epsilon over r naught mg cot theta minus mg cot theta. So you see what's happening. The mg cot theta term cancels out. And I just have this nice looking term here. The m cancels out on both sides. There's still r naught cubed there, sorry. So the m cancels out on both sides. And I have epsilon double dot. I can bring this to the other side. So that's plus 3 epsilon over r naught cubed. And here, cosecant squared theta, when brought to the other side, becomes sine squared theta. So I get cos theta over sine theta, that's cot, times sine squared theta, equal to 0. I should have left it as cot, because what I'm going to do now is put r naught from here. So when I put r naught cubed, that's got a cot there, that will cancel with a cot there. So just pretend I didn't write cot as cos over sine. Okay, so I'll do that next step. Epsilon double dot plus 3. I put this for r naught cubed. So what I'm going to decide to do instead of what I just did is the following. I'll indeed cancel the mg cotangent theta by writing this as equal to that for the first term. But for the second term, what I will do is I'll write it back as LZ naught squared over M R naught cubed. Okay, so I'll do that. So I canceled it. So I'm rewriting it as that. This is just epsilon over R naught. There's no cube there. And now I'm going to rewrite mg cot theta as all of that. So this becomes LZ naught. So this equation is just to be ignored. Okay, don't worry about this equation. So I get bring everything to this side and divide by cosecant squared theta. I get 3 LZ naught squared. So I put that back in there for mg cotangent theta times sine squared theta, that comes from this, brought to the other side, divided by m squared. Because if I bring this back, the m doesn't cancel anymore. So that's an m squared, r naught to the 4, epsilon equals 0. So I canceled the mg cot theta, but I did not cancel the m's. So you should imagine this m to be still there. And then I brought back mg cot theta. So I apologize for that unnecessary writing here. Perturbation theory is tricky. There. Now this is great news because this here is just the angular frequency of the perturbation squared. All right, we can identify something like that. Now, when I have something looking like that, I get a little queasy because the units may not work out. So I'm going to check the units. The units of angular momentum are joule seconds. So the LZ squared is going to be joule squared second squared. Sine has no units. mass is kg squared, m squared is kg squared, and that's meter to the 4. Let's hope this is same as 1 over second squared. Joules is like kinetic energy, so it's going to be kg meters squared over second squared. If I square it, I'm going to get kg squared meter to the 4 over second to the 4 times second squared divided by kg squared meter to the 4. Well, great. The kg squared meter to the 4 cancels out. I get second squared over second 4, and that's 1 over second squared. So we are home free. So this has actually shown us that the radial perturbation is a constant. It's not constant, it's stable. So we can solve this equation. The equation I have is epsilon double dot plus omega p squared epsilon equal to 0. And the solution is obviously cosine or sine. I'll write it like this: epsilon equals epsilon naught cosine omega pt plus delta. So it's a bounded perturbation, and the bound is between r naught minus epsilon naught to r naught plus epsilon naught, because cosine is bounded between -1 and 1. So we have shown that it's radially bounded. In terms of a figure, what this would look like is if you perturb this, the orbit will change from being a perfect circular orbit to something that looks like this. Now there's a question of whether it'll close or not. So that's our next thing in analysis. Do these perturbed orbits close or not? But we'll come to that towards the end. Now there's a slight, the second perturbation I talked about is the perturbation in the angular momentum. So let's do that next. Here, remember that p phi is mr squared phi dot, and that's LZ naught. LZ naught never changes, but what we can change, we have just changed r, we can also change phi dot. So I'm going to say that phi dot is phi dot naught plus some psi dot, with the same stipulation that psi dot is much less than phi naught dot in absolute value. So once I have made that condition, I can write down the new angular momentum. It's still the same as the old angular momentum, but now in terms of the perturbed variables: r naught plus epsilon squared times phi naught dot plus psi dot. Well, by the same binomial theorem, that's m r naught squared, 1 plus epsilon over r naught, and when I square it, I get 1 plus 2 epsilon over r naught. So I have to put this approximation sign, times phi naught dot plus psi dot. Now psi dot is very small, epsilon is very small. That term with epsilon and psi dot can be neglected. So we only have 3 terms. Let's write them. So this is m r naught squared times phi naught dot plus psi naught dot, no naught, psi dot, plus 2 epsilon over r naught times phi dot naught. Now, by the way, this quantity mr squared phi naught dot is just, again, LZ naught for a circular orbit. So this is LZ naught back. The first term is LZ naught again. So this is LZ naught plus mr squared psi dot plus mr naught squared times 2 epsilon over r naught phi dot naught. So that's all equal to LZ naught. So LZ naughts will cancel, and I'm going to get 0 equals a bunch of stuff. Now mr squared can be canceled, so I get 0 equals psi dot plus 2. Now for phi dot naught, I can put it equal to LZ naught over mr naught squared. So let me just do that. And when I do that, I get r naught cubed because of the r naught already here. This mr squared is canceled. So I have this beautiful equation times epsilon. Now this is actually going to prove for us the perturbation is stable in the angular velocity also. So I'm going to get psi dot equals negative 2 LZ naught over m r naught cubed. And if you wish, you can take the r naught from here, cube it, and put it back there. I won't go that route. I just don't want to lengthen this video unnecessarily, times epsilon. And that immediately tells me that this also is bounded, because this is given by epsilon naught cosine omega pt plus delta. So also stable. So the last part of our video today is to find the condition, the quantization condition for orbits to be closed. Orbits are closed precisely when m times going around will coincide with n of these up and down bobs, which I'll call nodes. Okay, so let's write the criterion for closedness. Time for m orbits, and m is an integer, not to be confused with mass. Now I'll see that the mass will be a problem. So what I'm going to do is I'm going to call the mass by capital M from now onwards. Okay, time for little m orbits will coincide with time for n, also an integer, perturbation nodes. This up and down motion is called a node. So we can write this criterion as follows. Time for m is 2 pi m over phi naught dot, that's m orbits. Time for n nodes is 2 pi n over omega sub p, with omega p defined somewhere over here. Omega p squared is that. So this can be solved. So I'm going to get 2 pi's cancel out, and I get omega p squared. Because omega p squared is easier to write, I'll write omega p squared is equal to n squared over m squared times phi naught dot squared. Now I'm going to put omega squared from here, except that m is going to become capital M. So watch out for that. The 3 LZ naught squared sine squared theta divided by m squared r naught to the 4. And all that will be equal to n squared over m squared times phi naught, which is LZ naught over mr squared. When I square phi naught, I get LZ naught squared over m squared r naught to the 4, capital M. So this completely disappears, LZ naught squared completely disappears, and we have an amazing criterion, which is 3 sine squared theta equals n over m squared. Just marvel at this, at the beauty of this. This tells me that sine theta is going to be 1 over root 3 n over m. Only angles that satisfy this weird condition will result in closed orbit. So if you want to convert this problem into quantum mechanics, this is the starting point for you to consider the Bohr-Sommerfeld quantization.